here is the definition of a polynomial function. So a polynomial function f of x is just that, a polynomial. In this definition, you have three terms: ax to the power of n, bx to the power of n minus 1, cx to the power of n minus 2, and you may continue it and on and on and on. And I wrote down these definitions here, so let's go through them quickly. So first of all, the leading term. The leading term of a polynomial function is the term, and remember the term is this whole thing here. The ax to the power of n is the term, the bx to the power of n minus 1 is the term, and so on. So the leading term is the term that has the variable in its highest power. So I want you to look at this quick example of function g of x, which is a polynomial function. It has three terms, the first one, the second one, and then the third one. And the question is, what is the leading term of this function? So what you're looking for here is the term with the highest power of x. And that is this last term, because that's the highest exponent that x has, is x to the power of 4. The rest of them have x to the powers that are lower than 4. So this will be the leading term, x to the power of 4. Now the leading coefficient is the coefficient of the leading term. So when you're asked for the leading coefficient, you are only looking for the number in front of the x with the highest power. So going back to this function g, if this is your leading term right here, x to the power of 4, what is the number or the coefficient in front of this x with the highest power? That's a 1. So 1 here is the leading coefficient. So the leading term is the entire 1x to the power of 4. The leading coefficient is just that number 1 that's in front of that x to the with the highest power. So the degree of the polynomial now is the exponent that is the highest. So for this function g, the degree will be 4. It's the highest power of x. When you're answering questions about the degree of a polynomial, make sure you don't say x to the power of 4. You have to say 4 is my degree. Okay. I do have a few other definitions here within the polynomial degree. So sometimes you may see the words linear polynomial. That means the degree is 1. The degree of that polynomial is 1. There is quadratic, and you've seen those before. That's the second degree. Cubic is third degree, and there is quartic polynomial. That's fourth degree. So for instance, this one here is the quartic polynomial because the degree of it is 4. The next thing is the end behavior of the function. What it means is how the graph will look on its ends, on the very far left and on the very far right of your x-axis, very far left and very far right. And what it depends on is your leading coefficient and your degree. So the leading coefficient, remember, leading coefficient is the coefficient of the leading term. Like for function g, that was a 1, and then the degree is the highest power of the variable. So for function g, it was 4 here. So let's look at the 4 options and how they play out depending on a, the leading coefficient, and n, the degree. So for this first one, the end behavior will look like this. If a is positive, so if the number in the front of the highest power of x is positive, and if n, which is your degree, is even. And the great example of such end behavior would be a parabola. If you think of a quadratic function, we talked about it before. If the a in front of that quadratic function is positive, and we know for the quadratic function n is 2, which is even, this is the parabola that opens up. You may have higher than 2 of a degree, but as long as it's even, the ends of your graph for that polynomial function will look like a parabola. So similarly, a is negative, so n is still even, meaning 2, 4, 6, 8, and so on, but a is now negative. This will look sort of like a parabola, but branches will go down, so up and down. That would be the end behavior. If n is odd, and this one here, if n is odd. So this rising graph is for the positive a, and this descending graph is for the negative a. Both of them, however, have an odd end. So the next thing that I wanted to talk to you about is the zero of a polynomial function. The zero of a polynomial function is the value of x that turns that function into a zero. And then here I have graphically a zero is where the graph crosses or touches x-axis. Finally, the multiplicity of a zero is how many times a particular number is a zero for that particular function. And I'll show you how to find it. It looks more complicated than it really is. So these are the definitions, and I have a few examples here that we'll go through. So with this function h and then function k, we are going to try to find the leading term, and then based on the leading coefficient and the degree of our polynomial functions, we will determine what type of end behavior these functions will have on the graph. So let's look at function h. First of all, let's find the highest exponent that x has in this function. This exponent is 3. X cubed is the highest power of x, meaning the leading term of this polynomial function is negative square root of 5x to the power of 3. All you care about when it comes to end behavior is what leading coefficient the function has and what is the degree of that function. So the leading coefficient of this function is negative square root of 5, and the degree of this function is 3. What it means for us is that the leading coefficient is negative and the degree is odd. So the end behavior of this function can be described as follows. Now let's look at function k. What is the leading term of this function? The leading term is the term with the highest power of x, and that is pi x to the power of 4. Now, what is the leading coefficient of this function? The leading coefficient is the coefficient of the leading term, which means it's pi. So the leading coefficient is pi, and what we really care about is its sign, and it's positive. What is the degree of this polynomial function? The degree of this polynomial function is 4. So looks like we have a positive leading coefficient, positive number here, and the even degree. What it tells us is the end behavior of this polynomial function will look like this. So this polynomial function t of x, I'm going to ask you to find the zeros of this polynomial function and determine the multiplicity of each zero. When you're asked to find zeros of polynomial functions, they must be in factored form, which this function is in factored form. So what we need to do now is we need to take each factor, very similar to quadratic equations, set each equal to 0 and determine what our x's are. Those x's will be the zeros of our polynomial functions. So it looks like here this function is in factored form. We have 1, 2, 3, 4, 5 factors here, with the first 3 being identical. So you have x plus 1, x plus 1, and x plus 1 listed here. They are the same. Another way and shorter way to write this function would be x plus 1 to the power of 3. So we're going to take the first factor, which is x plus 1, and we're going to make it equal to 0. If x plus 1 is equal to 0, that means x is equal to negative 1. And that takes care of these 3 factors. So then I'm going to take the next factor, which is x minus 3, and I'm going to make that equal to 0. If x minus 3 is equal to 0, that means x is equal to positive 3, and that's our second 0. Finally, I'm going to take the last factor, which is x, and make that equal to 0. Well, this one does not require any solving. It's done. X is equal to 0 is the 0 of our polynomial function t of x. So we have 3 different zeros. And now what's left to do is to find the multiplicity of these zeros. The multiplicity of zeros is determined by how many times that 0 appears inside of the factored form of your polynomial function. Specifically, what you're looking at is the exponent of the factor that gave you that 0. So it looks like our first factor, x plus 1, appeared in our polynomial function 3 times. That means that the multiplicity of 0, x equals -1, is 3. Let's look at the next 0. The next 0 is x equals 3. How many times did the factor that produced this 0, x equals 3, appeared in our polynomial function? Looks like 2. So the multiplicity of this 0 is 2. Multiplicity is 2. Finally, how many times did the factor that produced the 0, x equals 0 for us appeared in our polynomial function? And the answer is 1, because it's x to the power of 1. So the multiplicity here is 1. Why is it important to know what is the multiplicity of 0? The multiplicity of 0 can tell you what happens with the graph of your function at that specific point on x-axis. Specifically, if the multiplicity of your 0 is even, meaning 2, 4, 6, and so on, the graph will touch or will be tangent to the x-axis at that point. So we have 2 zeros with an odd multiplicity, this 0x equals -1, and this 0x equals 0. So multiplicity of -1 is 3, which is odd, and the multiplicity of this 0 is 1, which is also odd. So what it tells us is that those zeros, your graph will actually cross x-axis, meaning it will go from being below x-axis to being above, or vice versa. Here is another example of a polynomial function with the leading term 4x cubed and leading coefficient of 4 and the degree of 3. Remember, if the leading coefficient is positive and the degree is odd, the end behavior would look like this. The problem with this polynomial function is that it's not in factored form, and for us to be able to find the zeros, we have to factor it. Because you have 4 terms, most of the time 4-termed polynomials can be factored by grouping. So that's what I'm going to do. I'm going to group them 2 at a time, meaning I will put parentheses around the first 2 and then around the last 2, and I will try to find the greatest common factor for each group. Well, I created the 2 groups using the blue sets of parentheses, and now I will try to factor out the greatest common factor from each group. So it looks like the greatest common factor for this group is x squared, so I'm going to take that out, x to the power of 2, which leaves me with 4x minus 1 inside of the group, minus 144x plus 36. What do those two have in common? Well, 36 actually goes into 36 and 144. So I'm going to take 36 out. And once I do, that leaves me with 4x, because 144 divided by 36 is 4. And you still have the x. And then 36 turns into 1. Now, I'm going to write minus 1. Used to be plus 36, but 1 actually turns into negative because of this negative symbol in the front. So now you notice that you have 2 groups of 4x minus 1. We're going to place one of them to the front. And then the stuff that is not matching, the x squared minus 36, will go into the second group. So we're done factoring by grouping. However, I need to look at each of my factor and see if maybe I can factor further, and I can. X squared minus 36 is actually the difference of squares. So x squared is x and 36 is 6 and 6. So this will produce x minus 6 and x plus 6. So 4x minus 1 stays as is. And then x minus 6 and x plus 6 here. Remember, this is now the factored form of our function f of x, and we factored it with the purpose of finding zeros and then the multiplicity of each zero. To find the zeros, we have to take each factor and make each of them equal to 0, and then solve for x. So I'm going to take 4x minus 1, make that equal to 0. This means x is positive 1/4. I'm going to take x minus 6 and make that equal to 0, which means x is 6. Finally, if I make x plus 6 equals 0, x will be negative 6. These numbers are the zeros of my polynomial function f of x. What it means is the graph of this function will either cross or touch the x-axis at those points, depending on their multiplicity. The multiplicity of 0 is how many times the factor that produced that 0 appears in our function. In other words, the degree of that factor. So we have 4x minus 1, that's our first factor, and the degree of it is 1. 5x minus 6, that's our second factor, and the degree of it is also 1. And we also have x plus 6 with the first degree also. So the multiplicity of each of these three zeros is 1. 1 is an odd number, so each one of these zeros has an odd multiplicity. What it means is the graph will be crossing x-axis at those points. So if I were to sketch the graph of this function, I would place my zeros, the points on x-axis that I just found, and also the end behavior. Remember, I mentioned in the beginning that the end behavior of this function will look like this, based on the degree of that original function and the fact that the leading coefficient was positive. These would be the ends. And then I know that at each of these points, my graph will cross x-axis because each of them has odd multiplicity. So if I were to graph it, it will look like this. So finally, this polynomial function q of x, it's the same exact question. The end behavior will depend on the leading coefficient, which in this case it's 1, because that's the number in front of x to the 4th, and then the degree, which is 4, and that's an even degree. So the end behavior will kind of mimic the parabola. It will look like this. So now let's find the zeros of this function. To find the zeros of this function, you have to factor it. It looks like a quadratic trinomial, but it's of degree 4. So when you're factoring it, instead of x in each factor, you actually will write x squared in those factors. And that will take care of the fact that it's x to the power of 4 versus being x to the power of 2. Okay, so this here requires us to find two numbers that multiply to 75 and add to negative 28. Those numbers are negative 25 and negative 3. So negative 25 times negative 3 is positive 75. And negative 25 plus negative 3 is negative 28. So this thing here factors into x squared minus 25 and x squared minus 3. Then you need to see if any of these factors can be broken down even further, and they can. X squared minus 25 is the difference of squares. This is x times x, and this is 5 times 5. So you can break this down into x plus 5 and x minus 5. And this here is not the difference of squares, so I'm going to leave it as is, but we will be looking at it still and trying to make it equal to 0 and solve for x with the hope to find an extra 0 of our polynomial function. So I'm going to leave it as is, x squared minus 3. Okay, So now we're ready to find the zeros of our polynomial function. We will take each factor, which we have the 3 of them, and we will make them equal to 0. So let's make x plus 5 equal to 0. If x plus 5 is 0, that means x is negative 5, and that's the first 0. Then we'll make x minus 5 equal to 0. If x minus 5 is 0, x is 5, and that's our second 0 of the polynomial function. Finally, x squared minus 3 equals to 0. To solve this, we're going to take the negative 3, place it to the other side, make it a positive 3, so x squared equals 3. And then finally, to get x by itself, I need to remove the square. And in order for me to remove the square, I need to square root each side. So I'll square root the left side, which will produce an x. And I will square root the right side, which will actually produce two answers, a positive square root of 3 and a negative square root of 3. So x here is either a positive square root of 3, or it also may be a negative square root of 3. So this factor produced two separate zeros for us. Now let's determine the multiplicity of each one of these zeros. Remember, the multiplicity of the zeros is how many times the factor that gave us that zero appears in the factored form of the polynomial function. So the first zero is x equals negative 5. That was produced by the factor x plus 5, and it appeared one time because the power of it is 1. So the multiplicity of this zero is 1. X equals 5 is the second zero, and it was produced by the factor x minus 5, and that factor also only appeared one time because the power of it is 1, so the multiplicity is also 1. This factor here produced two separate zeros for us. One is negative square root of 3 and one is positive square root of 3. On the graph, by the way, when we're graphing these zeros, positive square root of 3 will approximately be 1.7, and negative square root of 3 will approximately be negative 1.7. That's for the graphing purposes. So how many times did these zeros appear in our polynomial function? Well, each of them only appeared once. Okay, so for the graph of this function, I already placed the zeros that we just found on x-axis at negative 5, at positive 5, at negative 1.7, and then at positive 1.7. I will now place the end behavior on the graph. The end behavior was, remember, looking like this. So I'm going to place those branches here and on the end here. Okay, so given the fact that the multiplicity of each of the four zeros of our polynomial function is 1 and it's odd, the graph will cross x-axis at each one of these zeros. So I'm going to do just that. And here is the sketch of the graph of our polynomial function q of x.